Can I now move on to our second speaker, who's David Churcher from BSRIA. David has more than 20 years' experience of working with the buildings and construction industry. He's got a degree in civil engineering and completed his MBA in 2005. As well as being an expert facilitator, most of David's professional work at the moment within BSRIA is on life cycle costing. David.
Thank you very much, Richard. In the short time I've got available to me this morning, I have the unenviable task of giving you an overview of life cycle costing as a topic. And I can no way do that justice by going into lots of different concepts in great detail. So what I'm going to try and do is to focus on these four key concepts which together underpin the principles of life cycle costing. Andy's already given us an insight into the practical applications of LCC. What I'm going to try and do is support that with some of the theoretical underpinnings. The first thing I want to talk about is the issue of timing. It's a key concept within life cycle costing, actually given to it by its name, life cycle. We have to try and work out what that life cycle is, what it means, and how we might determine it. Sometimes the life cycle is determined by the driver, which is behind the analysis in the first place. So for example, if you are carrying out a BREEAM assessment, the Building Research Establishment Environmental Assessment Method, and you want to get the credits for doing life cycle costing, then they stipulate that you will need to do your analysis for over a period of 60 years. That may or may not have anything to do with the project that you're actually concerned with, but tough. That's what they say, so that's what you've got to do if you want to get the credits. In other instances, you may have more choice over the period of time that you want this life cycle cost to be carried out. For example, it may be linked to the remaining period you've got on the lease of a building that you're refurbishing. Or if you're the developer, the period of time you want to be letting it to a tenant. Sometimes if you're maybe looking at a very focused life cycle cost analysis, then you can try and link your study period to the life expectancy of the major pieces of equipment that you are going to be dealing with. That sort of makes sense if you're only interested in the heating system, the cooling system, the lighting or whatever. Just analyse it for its life expectancy. And there's quite a lot of information generically, but also that can be customised to tell you what that sort of life expectancy might be, and is already hinted at some of them in terms of the information that CIBSE produces. The other thing that we need to think about is the fact that we have a timeline. So different events are going to occur over the timeline, and those events can be divided into different groups. There are going to be events that happen immediately. Your capital investment, whether it's design, your construction and installation costs, the things that we're actually normally quite comfortable with assessing when we want to understand the economic attractiveness of a project. But we also need to introduce some of these other activities which carry on throughout the life cycle, and Andy has already alluded to some of the headings as well. For example, we'll have annual cost activities like energy or staffing or reactive maintenance. We might have regular or periodic single items of expenditure which happen when you need to undertake a major refurbishment or indeed a replacement of equipment. Again, linking back to what is the life expectancy of that particular piece of kit, and we'll come on again to think about how comfortable we are with some of those figures that we find in the references that we can look up. And because the study period is sometimes a little bit of an artificial choice, then it doesn't necessarily end with the date on which the building or the asset ceases to exist, so that there will be some future use of the asset and the materials and components within it. So you can then provide yourself with some end-of-study benefits in the sense of residual value of equipment or materials, which in effect give the analysis a credit for the unused portion of the assets that are going to go on to be used in some other way. It's often very easy to try and lay this out in a very simple histogram. Here we have an illustration of two different heating systems using two different types of boiler with red bars and blue bars. I've composed this particular example over, if you can see that, a 30-year period. So we're starting at the beginning with year 0, going all the way out to year 30. We've got some initial installation costs, your investments of purchasing the boilers and installing them for the first time. We've got reinstallation when the boilers wear out and need to be replaced. And you can see that these two, the red and the blue, they're on different life expectancies. The blue boilers are going to last for 10 years and the red boilers are going to last 15. And that's for whatever reason, but we're comfortable with putting that into our analysis. And along the bottom here, we've got all of the annual costs all linked together, all grouped together into a single figure for ease of illustration. But these are the energy costs of running the boilers. And again, we've got some slight differences between the red and the blue scenarios. And a technique like this is often very, very helpful in making sure that the person who's doing the analysis hasn't missed out something critical, as is often the case. And if that happens, then obviously the analysis is off to a bad start. Andy's already said something about the sources of information, so I'm not going to dwell on that at the moment. I'm going to press on. That's timing. Timing is one very important aspect of life cycle costing. Another very important aspect is money. How do we compare different cash flows of costs and benefits? They didn't exist on that particular timeline, but they might be there, so that we can actually really compare option A, alternative A with alternative B. We do this through the use of present value. We're using a mathematical technique called discounting, where we are taking the future costs in our timeline, each of those little bars in the histogram, and bringing them back to an equivalent value today. To do this, we need to decide on this figure called a discount rate. And what the discount rate is trying to do is to quantify the rate at which value decreases over time. Not just because of inflation, because that is there as well, but it's actually built into us as part of the human condition almost, that we want our benefits today rather than tomorrow. If you don't quite get that, ask yourself the question whether you would rather win your lottery this coming Saturday or in 5 years' time. I can guarantee that the majority of you would rather win the lottery sooner, thank you very much. It's the same principle. You might get the same amount of money with the same purchasing power, but having the money earlier gives you more flexibility, gives you more options of what to do with it. And that changes your perception of what that amount of money means in terms of value. In life cycle costing, we're also trying to simplify things as much as possible. It may not sound like it, but we are. And so what we're trying to do as well is to strip out any unnecessary complication. One of the complications we can usually strip out, particularly when we are trying to compare different alternatives economically, is this idea of inflation. It's across the board, it applies to everything, and so because of that, we can ignore it. It means that the figures that we're using don't represent actual money anymore, but we have to keep that in mind, of course. And we do that by using what is called a real discount rate. A real discount rate is the difference between what it's going to cost you to borrow money to fund the project, assuming you have to go out to the market to get the capital sum required, and how that is going to be eroded over time by the effects of inflation. This is actual end-of-year information. The black line is the retail price index in the UK at the end of every year from 1975 up to 2011. The red and the green lines, apologies if they might be a little bit faint, are the borrowing costs for the public sector in green and for a blue chip corporate client in red. And what we're trying to estimate is the difference between the borrowing line and the inflation line. And that gives us our figure for a discount rate. As you can see, it changes from year to year. It changes from month to month. It changes probably even more frequently than that, but we can't obviously cope with that, so we try to estimate what this gap is over a period that is consistent with the study period that we've already talked about. For public sector, it's very easy. We have a 3.5% discount rate. It's laid down by Treasury. We use it. It takes away all of the complications. For private sector, we have to make this judgment ourselves. Sometimes we might get a rate that is a little bit above the public sector. Sometimes that rate is a lot above the public sector, and the difference is usually how creditworthy is the client that's got to borrow the money. But you have to have this number, otherwise you can't move any further forward. The rub is that when you apply these different discount rates to the costs that you're going to be incurring over time, then they have different effects. So if you are lucky enough to be working in the public sector or for a public sector client, you have a 3.5% discount rate. Your £20,000 investment, which might need to be made in 15 years' time, because that's when you've got to replace the air handling unit, by the time you get to year 15, is actually then only got a net present value of £12,000 in part of your calculations. If you're in various parts of the private sector with less and less good credit ratings, then your net present value is getting significantly less each time. By the time you get up to a 10% discount rate, over 15 years, your £20,000 investment has got a net value of only £5,000. So picking that number correctly is patently an important part of getting the overall outcome correct. It's therefore no surprise, I think, that in the whole topic of life cycle costing, there is a big issue with uncertainty. Life cycle costing is essentially all about being approximately right. And in some of the later presentations, this topic is going to be revisited in much more detail. So I'm only going to be looking at this from a very sort of high level and, I suppose, quite simplistic point of view. The important thing to realise is that uncertainty is everywhere. We're building these models of how we think particular alternative projects might behave, when the costs are going to arise, how big those costs might be, and how we're going to be discounting those costs over time. And we can have uncertainty anywhere. It may be that we're not so sure about our discount rate. It may be that we're not so sure about how long this study period is. You start changing the study period, and obviously some activities might drop off the end of your analysis. That's very helpful if you want to reduce your costs in terms of comparing one alternative with another. But of course you need to make sure that you're still comparing like with like. It may be that you've got variation in a particular type of cost item. I'll come on in a minute to say something about energy, which is perhaps the most crucial and most obvious area of variability. It may be that you've got uncertainty in the way that the study is constructed. If you're trying to compare a traditional design with an innovative design, then I think it goes without saying that you might have quite a good feeling, even if that's as good as it is, about the life expectancy of a traditional boiler, the costs of maintaining and running a traditional boiler or air handling plant. If you're trying to compare that with an innovative product, which has maybe only just come to market, there isn't going to be the history or the experience to really tell you how long that bit of kit's going to last. You've got to make a guess. You may or may not be right. So you need to find a way of then accommodating that uncertainty in the way that the analysis is carried out. And on top of all of that, there are going to be all these other areas of uncertainty too, because the world doesn't stand still. And the way that we traditionally think about lifecycle costing is that we have the world today, and we plan for it to be the same for the next 30 years. We'll be replacing these lights with the same lights every time they blow. We'll be replacing the boiler with the same boiler every time it's got to the end of its life. Obviously, in reality, that's not what you would do. But in the absence of a crystal ball, then so far, that's all we've really been able to practically achieve. So things like how technology changes, how legislation changes, where we are in the economic cycle, whether your contractors are anxious to do the work for you or not, will obviously affect the prices they quote you, and that feeds through into the costs that end up in your model. All these areas of uncertainty, needless to say, an awful lot of variability in the outcomes that you can expect. This is energy. And again, these are actual figures, but normalized. So I've got, sorry, the yellow is very faint. I've got 4 different sources of energy. These are UK figures collected quarterly by the Department of Energy and Climate Change. And there's a baseline of 2005. So if every source of energy cost 100 currency units per energy unit in 2005, then this chart will show what was the relative cost prior to that and since that. I don't think anybody will be surprised to see that all sources of energy have got more expensive. And this is after inflation has been stripped out of the numbers. So this is real cost. For example, look at the pink line. Gas is now almost twice as expensive in real terms as it was in 2005. But you go back 10 years before that, and actually it was pretty much the same. It dipped in the middle and came back up, but essentially it didn't move very much. If you were doing an analysis in 1995, and you had assumed that in 10 years' time your cost of gas was going to be the same, you wouldn't have been very far from the truth. If, on the other hand, you were thinking about oil, you'd have had a very different story. Although it's, again, still got much more expensive, this is the green line now, since 2005, up by 75%. In the 10 years prior to that, it increased by about 80%. So if you're trying to compare an oil-fired heating system with a gas-fired heating system, then you need to find a way of accommodating that change in the way that energy prices move. And of course, the real rub is that this is all history. It's not a great deal of help to us in trying to predict what the future is going to be. So it comes with a health warning, even though we might still use figures like this to try and help us. How does this uncertainty actually come out in the numbers that we might end up with? Well, this is the timeline that I started with, the red and the blue boiler systems. I've done the calcs, I've crunched the numbers, I've allowed myself a 6% discount rate, and these red and blue dotted lines are the answers that I get when I crunch those numbers. But if I'm at a period of the design process where I really don't know very much about the scheme, I might just be thinking about the philosophy of heating. So I won't actually know which particular model of boiler I'm going to choose, or I may just have an idea of what type of system it's going to be. The design is going to be very, very uncertain, not very fixed, and so there's likely to be a plus or minus 25% health warning on the life cycle costs that you calculate. And in this particular instance, what it means is that the blue and red systems have costs somewhere in these red and blue bands, and they now overlap. What that means is that we can't really tell them one from the other. We've got some overlap. We haven't got clear blue water between one system and the next. By the time we move slightly further on the design process, we've got more information. We've actually maybe gone out and got some quotations from contractors and suppliers and installers. We might have got to a stage where our level of uncertainty is now only plus or minus 5%. And now here, we've actually got a much more clear conclusion. We're looking, in this instance, for the lowest life cycle cost figure. That's the one we generally try to aim for. So in this instance, we can quite clearly see that the red system is going to come out as the best alternative. Now, the way that that pans out in any particular project is itself going to change in the way that the project is designed, the way that the information is collected. And finally, what I've been talking about so far has been using life cycle costing as a tool in advance of making a decision, as a tool which helps that decision become more robust. So what we've been trying to do is then compare alternatives against each other to make sure that we are recommending the most economic one to the person who's going to end up making that decision. And that's why we're focusing mainly on the lowest life cycle cost. But we can also use the information that we've collected to try and understand what the actual expenditure might be for the solution that we prefer. Because that's actually the answer that a lot of us want to get to. It's all very well knowing which is the best solution to choose, but actually we need then to also to try and understand what that's going to mean in budgetary terms over the forthcoming years. And there are some rules which we have to apply if we're going down one route rather than the other. If we're comparing alternatives against each other, then we're trying to determine the best economic alternative. It's important to realise that the calculations we make are not representing actual pounds or euros. It's all just a number. And it's whether one number is bigger or smaller than another, and by how much. So what we're trying to do is focus on difference. Because we're focusing on difference, that means we can take shortcuts. We can simplify the models. If the two life cycle costs that we get out of our models are that far apart, it doesn't really matter whether they're up here or down there, provided that the difference is still the same and that it's significant. And the way that we get those costs, that we get those figures from up there to down there, is to strip out all the items of cost that appear on both sides of the equation. Because they're having the same effect on the model, whether you're looking at alternative A or alternative B. However, the situation is different when you're looking at how do I actually turn this into a prediction of what the future is going to be. Here we need to now focus on how complete all the items of cost are in the model. Have we picked up every single item? Are we really sure that we've got all the right costs in there to the same degree of accuracy? And we're not discounting anymore. We now have to start applying inflation as it really does apply throughout the future years to make sure that we actually come up with a figure of how much we're going to be spending, we think, in 2 years' time, 5 years' time, 10 years' time, by making a particular decision now. And there, I'm sure, we've all got horror stories in our minds and memories of clients or organisations who've made, for whatever reason, poor choices and have ended up paying for it. This is the technique which hopefully is trying to get them to avoid falling into the same trap again. The final thing to say is that lifecycle costing is not a once and for all activity. It's an iterative process which you might need to go round 2 or 3 times, even 4 or 5 times, before you're happy with the answers that you're getting. Bear that in mind and build that into the design of your study, so that you allow enough time and resource to actually tease out these details that I've been mentioning. Because it's without that, then the value of the end result is actually very limited. So that was just a quick whistle-stop tour of 4 of the key principles for life cycle costing, and I'm very happy to take some questions now if you've got them, or indeed later on the day.
Okay, thank you very much. Well, thank you, David, for that very comprehensive overview of life cycle costing. You've identified a range of factors which affect essentially the scope of the life cycle costing exercise being undertaken. For example, the length over which you consider it. Yep. You've also identified some of the key factors which affect the life cycle costing calculations, including the degree of uncertainty that you can get with some of that data.
More to be said about that later, I fear.
Well, that's good.
I hope.
And I think you've also given us some examples of how you can actually deal with uncertainty in terms of, for example, future costs. Also, what's come across to me from your presentation is that in terms of comparing life cycle costing options for different approaches, if you like, it's actually much easier than prediction. So,
well, yes, I think I agree with that.
Okay, so questions from the floor?
Thank you. It's Marina Cullingworth. I work for Mort, which is a social housing provider. And I was quite interested about what you were saying about the estimations of the lifetime of a piece of equipment, yes, and the uncertainty in terms of annual expenditure. And this is one of the biggest problems we tend to have within our flatted accommodation. And given the fact that we're going to be going more and more towards flatted accommodation, this is what I'm really interested in finding out is there any plan to try and measure these factors in terms of maybe actual maintenance costs, in terms of actually trying to find out or getting some sort of fault and outcome codes. I'll give you a specific example, I'm not going to go too much into it. Door entry systems. Mm-hmm. If you put into that uncertainty the human usage factor,
yes,
right, and you say to somebody, right, this door entry system is going to last 10 years, and in reality it lasts 5 years because of a percentage of vandalism which is like about 14% of annual cost. This has a major impact in terms of how we actually work out for any leaseholders in there the life cycle sinking costs.
Yes.
And this is something that I'm because we have lots of ways of measuring actual construction costs, but nothing in terms of trying to encourage contractors to feedback what actually causes a component to fail before the end of its expected lifetime. Is this any sort of software going to be produced that will allow us to do that?
Right, good question. I'm not sure how well I'll actually be able to answer it, really. I might need to seek advice from some of my colleagues. My gut feel is that there is experience and there is guidance which is published about what I'd call the mainstream building elements and construction systems. So yes, within, for example, the HVAC world, then there's quite a lot of understanding about the life expectancy of things which are essentially plant and equipment locked away so that they don't have this human intervention aspect.
Lifts are another classic example.
Lifts, absolutely, yes. I'm racking my brains to think of an obvious source of information which I can just point you towards, and I'm coming up with a blank at the moment.
Which is what I'm saying. I think there's a major void or vacuum within, because when you consider housing is such a major part of our built environment.
Yes, yes.
This is something that you have to put into any equation, is the actual element of human usage of a bit of equipment. And too often lifetimes and expectancies are all manufacturers, which is almost what I would call within a controlled environment.
Absolutely, yes. I mean, I'd probably draw a parallel with, there are networks that exist of building owners and operators and indeed service providers for exchanging that sort of information, which is essentially non-commercially sensitive. You know, everybody's suffering from the same problem. And I know those sorts of networks exist in general terms, so you might get university estates departments collaborating or exchanging information with each other so that they can have a bigger pool of knowledge from which to draw their conclusions. I'm not sure if there is the same thing in the social housing sector, though, unless anyone can correct me on that.
I was going to suggest, actually, you're probably in the best position to tell us.
Okay, so,
But certainly within a couple of years.
5 seconds just to say, if anybody wants to come and talk to me about that, I've got a knowledge transfer network hat on today, and I'd love to talk to you about getting housing associations together. Thank you.
okay, thank you for that. So with that, thank you ever so much for your time.